Hello, everyone, and welcome to day 5 of Jamb Physics in 40 days. The Jamb Physics in 40 days is a series brought to you by Oyalen, where when you dedicate 30 minutes to 45 minutes of your time daily, you will gather all the skills that you need to be able to ace Jamb Physics. So if you are a candidate that is preparing for the Jamb exams and physics is one of the subjects that you have registered for, then this video is definitely for you. So please do well to check out our videos from day 1, day 2, and up till this particular day, which is day 5. And also share it amongst your friends who are also preparing for the exams so you can help them to also ace Jamb Physics. Day 5 is about equilibrium of forces. And what Jamb expects all the candidates to understand before taking this exam, as far as this topic goes, are listed here in the subtopics. So we have that you must be able to understand equilibrium of particles. That is, for every particle to be stable, they must be under some forces that must balance out. And these forces are talked about especially when we look at the conditions for equilibrium. And then secondly, we have the principle of moment. We know that moment is force times distance, right? So that is the force acting on a body multiplied by the perpendicular distance. That's how we get moment. And there is conditions that we must consider also for this. So let's quickly go through those conditions. Firstly, for a particle to be in equilibrium, the forces acting upward must equal the forces acting downward. Or to put it in another way, we must say that the force acting in one direction must equal the forces acting in the opposite direction. For example, if you have an object here and then you pull to this direction with 10 newtons, it will continue in this direction unless you apply another force in the opposite direction. Now, if I should apply 10 newtons here, what will happen is that since these forces balance out, this object will not leave the spot where it is. So that is what we mean by equilibrium, to remain at a point unfazed by the force that are acting on it. So that's first condition. Now the second condition is that the algebraic sum of the moment about any point on the body must be 0. That is, when you take moment about an axis, if this is the axis that I'm working on, the clockwise moment must equal anti-clockwise moment. So let's put that down. Clockwise moment equal anti-clockwise moment. I'll soon explain this when we start solving questions on that. But these conditions must hold for anybody that is in equilibrium. And those are the conditions under the actions of parallel and non-parallel forces. Now, while working with these, there are some cases where you have the forces hanging at, for example, an angle to the horizontal, where we have theta. So you must also be able to resolve for the x component of a force and the y component of a force. So take note, f of x is always given as f cos theta, while f of y is given as f sine theta. Then finally, you should be able to understand center of gravity. Now, there are some shapes that we usually work with. For example, a meter rule. Now, there's a common question we find on this topic. Oftentimes, they will tell you something like a uniform meter rule is kept in balance. Now, when you hear the word uniform, first take note, if this is a meter rule, the center of gravity is often at this middle point here. So if it is uniform, that is from 0 to 100, the center of gravity will be at the 50 centimeter mark. But if it is not uniform, it could be at any other point, but it's always along this center here as well. So those are some of the things that we should also keep our eyes out for when we are solving problems on this topic. And it also applies to different other shapes, like if you are having a circular disc, the center of gravity is also here. If you have something like a cone, the center of gravity is along this part here like this. So, and then for the case of stability, there are about 3 types of stability that you should also be familiar with. We have what we call the stable equilibrium. we have the unstable, and then we have the neutral. So let me quickly give you an example of this. For example, if you take a ball, like a ping pong ball, and you put it in a bowl, if you displace it slightly, let's take this as the ball, and then I displace the ball that is initially here. If I displace it, what will happen is that it begins to roll about this point, and then in the end, it will come back to this same point where it started from. So every time you displace something and it always returns in the end to where it started from, that would be stable equilibrium. However, if I turn this bowl over now and place the ball here, you know that when I displace it this time, it will roll away from this point completely. So that is the case for unstable equilibrium, because it will move away completely from its stable point. However, if it were done on a flat surface like this, and I roll this ball a little, it will just turn and take stability at another point entirely. So that is neutral equilibrium, when it becomes stable at a different position, right? So you should be familiar with these three. There are some of those questions that you will find as we continue to solve past questions. So now that we've gone over this, get your materials ready. Let's solve some past questions on equilibrium of forces. This question from the UTME 2008 has three statements starting it off. The first statement says, all the three forces must be concurrent. Statement 2, the upward forces is equal to the downward force. And then 3, the algebraic sum of the moment about any point must be 0. Now the question is, which of the above conditions must hold for a body acted upon by a system of three coplanar forces to be in equilibrium? Now, when a body is acted upon by coplanar forces, and we say that such a body is at equilibrium, what that means is that there are some conditions that must be fulfilled. Now, the two conditions we often mention is that the force acting in one direction must equal the sum of forces acting in the opposite direction. And in this case, since we know that there are three forces, it means that if one is acting in one direction and two in the other, the sum of that two must give you what that one is. That is, if this is the object here, and one of the forces is going up and two down like this, if this is 10 newtons, then this has to give you a sum of 10 newtons as well. So it can be 7 and 3 newtons, it can be 5 and 5 newtons, it doesn't really matter. They just have to sum up to give you what you have up. And then the other condition we often mention is that the clockwise moment must equal the anti-clockwise moment, which can also be said as the algebraic sum of the moment about any point to be 0. So we mentioned 2 and 3. This statement 1 is also true, because for these conditions that we've mentioned to be true, all these forces must be acting at the same time. So that is, all the three forces must be concurrent as well. So all three statements, or three conditions rather, are true. So therefore, the correct option in this case is D. Here's another question from 2008 UTME. The diagram above shows the plank RS pivoted at its center of gravity O, and it is in equilibrium with weight P and Q. If weight 2P is added to P, the plank will be in equilibrium again by, now let's come to the diagram. So we see the plank and O being the center of gravity where the pivot is put, and then it is said that this plank is at equilibrium with these two weights added here. So we have P here and Q. So P is acting at point R and Q is acting at point S. Now, for this to be in equilibrium, now we must understand that the moment about this pivot must equal each other. That is, clockwise moment about it must equal anti-clockwise moment about it. And the clockwise moment would be Q multiplied by the distance between S and O. And then this would be P multiplied by the distance between R and O. So if we then go on to add 2P to this will become 3P. You know, that means that this has increased significantly by 3 of its value now. So that will make this drop to the ground at this point. However, if you want to balance it out, what can we do? we have to find a way to reduce this moment again so that it will become the same as this. And in order to do this, remember we are multiplying this by the distance, just as we are multiplying this by the distance here, right? So one thing to do here is to reduce the distance, because when you do that, then the multiple will drop down. Take for example, in this case, let's take this to be 4 for example, and this to be 5 initially. You know what we'll have here will be 5 times 4, which will give you 20. Now when you increase this by 3, it becomes 15, right? In order to make sure that you still get the same 20, so let's say 15 times r equals 20. You see that the distance r will then be 20 divided by 15, which is going to give us 1 point something thereabout. So you see that what we have here means that we have to reduce this 4 until it is smaller. So by so we are bringing p closer to O. So now when we look at our options here, we see that the correct one will be option B, which says moving p nearer to O. So we go with option B. A uniform meter rule weighing 0.5 Newton is to be pivoted on a knife edge at the 30 centimeter mark. Where will a force of 2 Newton be placed from the pivot to balance the meter rule? Now, before I go on to solve this, let me mention this, that this line of the question where we have where will a force of 2 Newton be placed from the pivot to balance the meter rule? Sometimes the question could be switched to where from one end of the meter rule should a force of 2 Newton be placed. So when you see those two, I will explain what they mean to you. So let's look at it. Now, first let's draw something to indicate the meter rule. Now, remember the question says a uniform meter rule, and a meter rule reads from 0 centimeter to 100 centimeter. And since it is uniform, it means that the weight is going to be acting at the center, which is at point 50 centimeter mark. So at this point is where the weight of the meter rule acts. And the weight of the meter rule is 0.5 newtons. Now, the pivot is placed at 30 centimeter mark. So let's come here, 30 centimeter, and then put the pivot. Okay, so once you put the pivot here, you will observe that the weight will drag the meter rule down in this direction. So in order to keep this at equilibrium, you must add another force on the opposite side of the pivot to balance it out. So let's say we put the force at this point here. Now the force itself is 2 newtons according to the question. Now, one of the conditions we have to apply here is the case where we have the clockwise moment and the anti-clockwise moment balancing each other out. So we can see that the distance here is, now when we take 50 minus 30, that will give us 20 here. So we don't know this distance, so let's call it x. So applying the clockwise and anti-clockwise moments equaling to each other, we will then have 2 times x equals, then on the other side, we have 0.5 times 20, right? So from here, we can then say x equals 0.5 times 20 divided by 2. Now, this would give us 0.5 times 20 is 10, divide that by 2, and then we have 5. So that tells us that the distance between these two is 5 centimeters. So that is going to be 5 centimeters from the pivot, right? So the correct answer there is option D. However, if you were asked how far from one end would it be, you will know that this one will be 5 centimeters away, which means it will be 0.25 here. So that is from this end to this point is 25 centimeters. So you see the difference there. And you can see that both options appear here. So get it right so that you don't mistake it. So in this case, it is from the pivot, not from one end. That is why we have gone with option D. This question from UTME 2009 says, which of the diagrams above shows the position at which a small ball bearing is in neutral equilibrium? Now, at the beginning of this video, while I was giving a crash course to this topic, We did mention that there are three types of stability you could have. We have the stable equilibrium, we have unstable equilibrium, and then we have the neutral equilibrium. Now, there are two ways I can describe this. I can use these images and I can also use other objects. Let's take, for example, if you have a cone. So when you have a cone, for example, that is standing on a circular end here, if it is standing this way, this cone is said to be at stable equilibrium. Now, how can we define this? That is, when you slightly displace the object, if it returns back to its equilibrium position, then it is stable equilibrium. Now, if I take the same cone and then stand it on its vertex like this, you know it's possible for it to stand like this. If you try real hard, it might just be there for a few seconds, right? But what we observe here is that if you just displace it a little at this point, what happens? It turns away completely away from its equilibrium point here. So that case is what we call the unstable equilibrium. And then when you have the same cone like this, now standing on its slant side, if I should just displace it a little, what will happen is that it will just roll and take equilibrium at a new position. Now this case is the neutral equilibrium. So once again, going over this, you displace slightly, it comes back to equilibrium position, that is stable. You displace slightly and it moves away completely from its equilibrium position, that is unstable. But when you displace slightly and it takes equilibrium at a new position, then that is neutral. Now to these images. We are trying to look for the one that is at neutral equilibrium, right? So let's displace them. If we should displace this, what will happen? It will begin to roll about and then in the end, it will balance at this point. That tells you it comes back to its equilibrium position. So it should be stable. So this one is stable equilibrium. In this case, it has been displaced, so it's going to continue to roll about and then come back to this point here, right? So in this case, what do we have? Here, once you move it, it will move away completely from this point and come and settle in the center. So this one would be a case of unstable equilibrium at this point. The same thing applies here because any slight displacement here, it will move away completely from its equilibrium position. So those are what? Unstable. But in this case, if we should displace this, it will just take equilibrium at a new point. So this would be the neutral equilibrium. So that is the correct option is D. So we go with option D. The figure above shows a seesaw which is perfectly in balance. The weight of the people sitting on it are 50 kg, X kg, and 15 kg. So these arrows here replace the image of the people. So instead of drawing the people, I have just represented their weight and the direction of their weight with these arrows. So that's their mass as shown. And they sit at distances of 1.5 meters, 1.5 meters, and 2 meters from the pivot respectively. So the value of X is, that is, we have to calculate the value of this X. Now, what we're going to apply here is that clockwise movement should equal anti-clockwise movement. And that will be sum of clockwise movement equals sum of anti-clockwise movement. Now, when we consider this image, the clockwise forces would be X kg and 15 kg that are acting clockwisely as they go in the clockwise direction. They will make this bar rather go in the clockwise direction. Whereas the 50 kg here will pull it to go in the opposing direction, that is anti-clockwise. So let's apply that. So we are having X kg multiplied by the perpendicular distance, that is this distance here, and that is 1.5, plus this other one also, which is 15 multiplied by the perpendicular distance, that is 2. And this equates with the anti-clockwise one. So we have 50 multiplied by 1.5. Now let's see what this gives us. This will be 1.5 x, right, plus this will give you 30 equals, now when we multiply this, what do we get? 50 times 1.5, this will give us 0, this will give us 25, this is 0, this is 5. So what we have is 0, 5, and then 7, so 75. Now from here we can say 1.5x equals 75 minus 30. That is what we'll have here is 45. Now x becomes 45 divided by 1.5, and that will give us 30. So that tells us that the mass of the person sitting at this point, which is x kg here, is therefore equal to 30 kg. So we pick option A. In this question, we're told that from this figure, that Mn is a light uniform metal rule, which implies that it does not have a weight, it is weightless. And it is pivoted at point O, which is 80 centimeter mark. So we have the pivot here. And then a load of mass 3.0 kg is suspended on the metal rule at point L, which is the 10 centimeter mark here. Now, if the rule is kept at equilibrium by a string Rp, so we have the string here, fixed at point P and attached to the rule at point R. Okay, so that this point is a fixed surface. Okay, now, and then we are told that the point where R is attached to the rule is the 20 centimeter mark. So we have to find the tension in the string. Now, take note, tension is the force along a string, right, that passes through the string. So, and it is measured in newtons. So if we are calculating in newtons, everything here has to be converted to newtons. So we know that 3.0 kg is same thing as 3 times 10, which will give you 30 newtons. That's taking G as 10. And then at this point, the tension in the string is basically going to be given as, so let's say the tension is T. Remember, we have to find the along the vertical part here. Okay, so what we have here basically is going to be T sine 30 degrees, because we are looking at the vertical axis. You know, this is also going to be the same as this. So when we consider this, we have the opposite here, and then this is the hypotenuse. The T here is at the hypotenuse, so we are looking for that along the y-axis. So that will be T sine 30. So this is what we have to use. So now let's go on to solve by applying the condition where the clockwise moment must equal anti-clockwise moment. Take note, this is the direction in this case. So we'll see that this is going to be moving in the clockwise direction. It will force this rule to move in the clockwise direction. So it's from here we're going to take our clockwise moment. So solution. Clockwise moment will then be this force here, that is T sine 30 multiplied by the distance. Now when we consider here to here, that's from 20 to 60, we get to 80 rather, that will give us 60. Now equate that to the other one here, which is going in the anti-clockwise direction, and the force there is 30 newtons. So 30 multiplied by the distance from 10 to 80, that will give you 70. So that is T sine 30 degrees equals 30 times 70 over 60. Okay, now what do we have here? 30 times 70 will give us 2,100. Now let's divide that by 60. So 0 cancels 0 easily. Now what do we have left? Now 6 in 21. 6 will go in 18 3 times. So remainder 3. Now 6 in 30, that is 5. So we have 35 newtons here. So which implies that the tension T would then be 35 newtons divided by sine 30. That will give us 35 newtons over sine 30 is 0.5. So, and of course, 35 divided by 0.5 will give you 70. So we have 70 newtons. So from the options, the correct is option C. The figure above shows two bodies of masses m1 and m2 in equilibrium under gravity. Now the tension in the upper string is, that is, we're looking for the tension at this point labeled T. So when we consider this diagram, the tension at this point is going to be m2 multiplied by acceleration due to gravity. But at this point, what we're going to have is this. Remember, this one is m1 times g. So at this point, we are having the addition of these two, the sum of these two. So solution, that will be m1, that is t, equals m1 multiplied by g plus m2 multiplied by g. Now, they both have g in common, so t is therefore m1 plus m2 all multiplied by g. So the correct option is option D. Now, this question from UTME 2023 says, three forces with magnitude 16 Newton, 12 Newtons, and 21 Newtons are shown in the diagram below, and then we have this diagram. So we have to determine the magnitude of their resultant and angle with the x-axis. Now, this is a case of where you have multiple forces acting on a particle, right? And to find the resultant, we have to find the x component and then the y component. So before we go on to show the solution here, let's take note. So the resultant is actually the square root of the x component, that is f of x squared, plus the y component squared. This is how we get the resultant. And we know that f of x normally is supposed to be f cos theta. And then f of y is supposed to be f sine theta. Now, another thing to take note of is that when you are applying sine, cosine, and tangent with multiple angles, such that we have different quadrants. In the first quadrant here, all of them are positive, that is sine, cosine, and tangent. But in the second quadrant, only sine is positive. In the third quadrant, only tan is positive. And in the fourth quadrant, only cosine is positive. So you have to take note of that when you are finding the f of x component or the f of y component of the forces. So let's solve. First, let's find the x component. So x will then be, starting with this. Now, this is between 0 to 90, so that's the first quadrant, and all of them are positive. So positive this, that's 12 newtons multiplied by cos, the angle with the x-axis is 32 degrees. Now, to the next one. We have 16, but this angle to the x-axis falls in the second quadrant. And in the second quadrant, only sine is positive. So that is, this has to take the negative sign. So it will be minus 16 newtons multiplied by cos 26 degrees. And then we come to this that falls in the final quadrant. And note, this angle here is 90. So in the fourth quadrant, cosine is positive. So we apply plus 21 newtons times cos 90 degrees. Now, from here, cos 90 is 0, so all of this tends to 0. But when you compute this, you will come up with negative 4.2 newtons. Now, let's find the y component. For the y component, starting with this, all is still positive in the first quadrant, so even though we are using sine, it will be positive. So that is 12 newtons multiplied by sine 32 degrees. In the second quadrant, sine is still positive, so plus 16 newtons multiplied by sine 26 degrees. And then in the fourth quadrant, sine becomes negative. So at this point, it will be minus 21 newtons multiplied by sine 90 degrees. Now, this will give you 1, and this will give you minus 21. So that means when we compute y here, what we are going to get is negative 7.63 newtons. which implies that our resultant becomes the square root of minus 4.2 in brackets squared plus minus 7.63 in brackets squared. And when you compute the whole of this, you will come up with 8.71 newtons. So we already know that the resultant is 8.71. That is, it could be this or this. Now let's find the direction. Now take note, the x component is in the negative. That is, when we resolve it, we're going to be going in the negative x axis, like this part here. So the resultant x force is going like this, and that is, the magnitude of the x component is 4.2. And then for the y, it is also negative, so it will be going down. So we'll come this way now. This is our y. And then what we have is what? The magnitude is 7.63. So please take note, this negative sign is only telling us that we're going the negative y-axis. And the negative for x says that we're going the negative x-axis. It does not mean that this is actually a negative value of force. It just tells us the direction it is going. So the resultant, since the angle between them is 90, is going to be this line drawn here, which would be the resultant we just solved as 8.71 newtons. Okay, so to find the angle that this makes with the x-axis, right, we just have to find theta. So if this is theta, that is tan theta is going to be the opposite, which is 7.63 over the adjacent 4.2, right? That is, theta therefore becomes tan inverse of this fraction, and this is going to give you 61 degrees. So now we have our answer, 8.71 newtons and 61 degrees to the x-axis, making the correct one option B. A block of mass 0.5 kg is suspended at 40 cm mark of a light metal rule AB that is pivoted at E, the 90 cm mark, and kept at equilibrium by a string attached at point D, the 60 cm mark, as shown in the figure above. So all the things I just mentioned, you can also see that from this diagram here. So we have to find the tension in the string, taking G as 10 meters per second. So that is, we have to convert this mass here into a force. So this would then be 0.5 times 10 to give us 5 Newton. Okay, and at this point here we have tension T. And to get the vertical component here, that is T of Y, would then be T sine 30 degrees. Okay, so applying this now, let's look at clockwise movement and anti-clockwise movement. So for the clockwise movement, that would be T sine 30 degrees multiplied by the distance between this point D and the 90 centimeters mark. Let's find out what the distance is at this point. So from the question, point D, the 60 centimeter mark, that is, this point is 60 cm. So the difference here is 30 centimeters. So we multiply that. And this equals, now to the other side we have this, which is 5 newtons multiplied by the distance from C to this point is 40, and that's 50. So what we have here is 50 centimeters. Now from here we can then say that sine 30 is 0.5. 0.5 T multiplied by 30 equals, now what do we have here? 5 times 50, this is 0, this is 25, so we have 250 newtons here. And then of course when we multiply this, what do we have? 30 times 0.5, that will give us 60. So 60 T equals 250 newtons. So T is therefore 250 newtons divided by 60. And this would give us 16.67 newtons. So the correct option is option A. Which of the following is an example of a couple? Now, when we say a couple, we're not looking at a husband and a wife. In physics, a couple has to do with two forces that are in opposite direction, but they cause an object to rotate about its pivot point. So that is, you have to apply two equal and opposite forces at two ends of this, and then it will cause it to begin to rotate about this central axis. That is what is called couple. So let's see which one of them is or are couples. Now, A says all of the above. So let's check the others. B says the force that are applied to the handle of a screwdriver when you twist it. And when you consider a screwdriver, it has an end like this that you have to apply force with two fingers here. One is pushing it this direction, the other one is pushing it in the opposite direction, as you see there. So one will be coming this way, the other in this direction, and you are making the screwdriver to turn about its central axis. So definitely that is a couple. C says the force that are applied to a cross wrench when you loosen or tighten the lug nut on a wheel of a car. Now, the cross wrench is that tool that we usually have at the trunk of your car that looks like this, okay, that we use to loosen the lug nut that is on the tires of the car. So when you want to loosen it, you have to apply a force to one of these bar, and the opposite force will be applied to the other side of the bar, and then you begin to turn it. So basically you're applying equal and opposite forces, but that will make this cross wrench to begin to rotate about its central axis. And that also goes with the definition of a couple. So in that case, it's also a couple. Then option D says the forces that are applied to the steering wheel of a car when you turn it. So that also is the same thing. So I assume this is a steering. You then turn, applying force in opposite direction that are equal, and it's causing the steering wheel to rotate about its central axis. So if all these three are coupled, then the correct option is option A, which says all of the above. This question from the 2024 UTME exam says, what will be the weight of a man of mass 60 kg standing in a lift if the lift is descending vertically at 3 meters per second squared? Now, before I go on to solve this question, if you're yet to subscribe to the channel, I want to implore you to please do so, because when you subscribe, you are helping us to be able to make more helpful videos like this and many more for those who would be needing it. So please do subscribe. It will only take a second of your time. Hit the subscribe button and also click the notification bell icon so that you get alerted every time we put out a new content for you. Now, to solve this problem, we have to consider that when a lift is moving freely, in this case here, the gravitational acceleration is going to act on it. So let's consider this to be a lift. It can either be going upward or downward. And the weight of a person is given as mg. The weight of anybody actually is mass multiplied by gravitational acceleration. Now, when you are moving either vertically upward or vertically downward, this weight changes. When you are moving upward against gravity, the W then becomes mass, then G plus the acceleration at which the lift is going up, right? And then when the lift is coming down, it becomes W equals M into G minus A. So take note of that. This is why we say that when the lift, the string holding the lift cuts, at this point, you know that this lift will be falling freely under gravity. So the acceleration will be equal to G. And if you apply that at this point, you see that G minus G will give you 0. That is why a person will feel weightless when it's in a lift that is falling freely under gravity. But do not forget, when it is moving upward, this is for upward motion, while this is for downward motion. And this is when it is on the ground. Or moving at constant speed. Okay. So with this said, let's go on to find the weight of this man. So in this case, the lift is moving downward and the acceleration A is 3 meters per second squared. So the weight would therefore be mass into G minus A because it is coming downward. So the weight becomes, mass is given as 60 kilogram. Then this is 10 meter per second squared minus A. A is given as 3 meter per second squared. So what we have here is 60 kg multiplied by 7 meters per second squared. And when we multiply, this would give us 420. And kilogram meter per second squared is the same thing as Newton. So the correct answer is option D. A body is pulled on a horizontal surface with a rope inclined at 30 degrees to the vertical. If the effective force pulling the body along the horizontal surface is 15 newtons, calculate the tension in the rope. So let's assume that this is the body, right? And then it is pulled with a rope inclined to the vertical. That is, this angle here is 30 degrees by a force to the horizontal here. So that is F of X is given as, according to the question, 15 newtons. So to solve this, to find the tension T here, we need to resolve this angle here. So this angle will be 60 degrees. Remember that this is a 90 degree here. So 90 minus 30 is what gave us this 60 here. So now let's go on to solve. So F of X is supposed to be F cos theta, which in this case is 60 degrees. So to find the F or T, as the case may be, so using this case, F would then be F of X over cos 60. So that is, we have 15 newtons divided by cos 60. And cos 60 is 0.5. So this is going to give us 30 newtons. Now from the options, the correct one is A. A uniform meter rule AB balances horizontally at 90 centimeters mark when a mass of 0.2 kg is suspended from B. Calculate the mass of the meter rule. So let's take this line to represent the meter rule. So A, B, which means this will be 0 centimeter mark. This will be the 100 centimeter mark. Now, it balances at point 90. So at this place, 90, let's put our pivot. Now, because it is a uniform meter rule, it means at point 50 is where the mass is going to be acting. So M would be here. And then the equilibrium force is placed at B according to the question. And this is 0.2 kilogram. Okay? So what we have to apply here is clockwise and anti-clockwise movement. So this would give us now M multiplied by the perpendicular distance. Remember, from 50 to 90, what we get here is 40. Equals, now here we have 0.2 multiplied by, the difference here is 10. So we have 40M equals 2, which implies that M is 2 over 40, which is basically 1 over 20. And this would give us 0.05 kilogram. So the correct option is option. This question says that we should consider the three forces acting at point O, and that this is actually at equilibrium as shown in this figure. So we have a point O here, and then we have three forces, P1, P2, and P3. So we are to find which of the following statements here, equations rather, is correct. So when you look at what we have here, we have this, take note, this is a vector case and the direction actually matters. So we see that P3 is going in this direction on the x-axis. So if we're going to do the same thing to resolve for P1 and P2, we have to find their horizontal forces. So in this case here, when we resolve this, what we should have is P1 cos theta. Now it is positive because this is in the first quadrant. Remember, in first quadrant, all is positive. Here, only sine is positive, which is the second quadrant. In the third quadrant, only tan is positive. And in the fourth quadrant, only cosine is positive. Okay? So, and when we consider this here, this theta 2 falls in the fourth quadrant. So, which means cosine is positive. So, this would be P2 cos theta. Now, if this were to be on another part, whether the second quadrant or the third quadrant, you will not be getting a positive solution here. And for this particle O here to be at equilibrium, the sum of forces must be 0. So that is, the forces acting in one direction must equal the sum of forces acting in the opposite direction. And this will be going along this x-axis here. So basically, P3 is supposed to equal this one here, which we have resolved to be P1 cos theta 1, and then plus P2 cos theta 2. So that's the only logical explanation for what we have here. So let's look at the equations we are given. We have P1 cos theta 1 equals P2 cos theta 2. This is wrong. P3 equals P1 cos theta 1 plus P2 cos theta 2. This is correct. Then P1 sin theta 1 equals P2 sin theta 2. This is also wrong. So the correct one is only the equation number 2. So looking at the options we have here, only 2 is correct. So we are going to go with option B. Now, if you're yet to subscribe, please ensure you do so, and also like the video and share it amongst those that really need this. Please ensure you subscribe, like, and share. The resultant of force of a couple is, so we have 4 options here. Now, let's consider a couple. Now, when we have a couple, it means that you have an object that is acted upon by 2 equal but opposite forces. Now, they are equal in magnitude, but their direction is in the opposite way. That is, if one of the forces, F1, is in this direction, the other force, F2, will be in the opposite direction. Now, and what this force causes this body to do is to rotate about this pivot point. So it will begin to rotate about this axis, right? So, and the condition here is that since F1 equals F2, the algebraic sum will then be F1. When this comes, it becomes negative F2 equals 0. The resultant is therefore 0. So the correct option to go for is option B. You can practice with more questions on the Exam Fun app, which is available on the Google Play Store and the Apple App Store. It's an app that makes learning very much fun. So go ahead and download the app, register, and then play, solve many questions that come from different subjects, from physics to maths to every other subject you could mention, and have fun. And the beautiful thing about it is that you also earn while you learn. So go ahead and download the app today and have some fun as you learn. And please do not forget to subscribe to the channel, like, and share the video. Thank you very much, and I'll see you in the next one.